And so this work is still kind of ongoing. So I'm happy to hear any feedback. I'm hoping to submit a paper on this within the next month or so. And so I've titled this work, Understanding the Relationship Between Tropical Cyclone Precipitation and Sea Surface Temperature. So just a first short intro. When you're thinking about the relationship between extreme precipitation and temperature, you can kind of think about it on like two different time scales. So first, there's kind of the like short weather time scale. So just like the instantaneous relationship between what the temperature is and then how much precip kind of falls at that moment. And so this relationship can depend on quite a few things, such as storm type, what the season, or any like very localized convective feedbacks. And in quite a few observational studies, they've actually found sub-daily precipitation increases above the expected like 7% per Kelvin baseline, the Clausius-Clapeyron relationship. Yeah, so quite a few studies in different places around the world have noted this, including, so in this figure on this paper, on this page, it's from Nealon et al. 2022, this recent kind of like review paper. And so, for example, you see in the green, this study, Lendrick et al. 2017, looked at above 90th percentile precipitation, I think in the Netherlands, I believe. And so they found that they had this relationship with dew point temperature that exceeded the Clausius-Clapeyron relationship. It was actually more like 14% increase per Kelvin, which is what that dotted red line is showing. And so then the other kind of flip side of things, the longer term relationship between extreme precipitation and temperature. So how is it changing on like a climate time scale? And so I refer to that as the climate scaling, whereas the kind of short-term weather time scale I refer to as the apparent scaling between extreme precip and temperature. And so then the other aspect of my work is obviously I look at tropical cyclones. And so when we're looking at observations of tropical cyclone precipitation, it's kind of tough to estimate these scalings. So for one thing, estimates of precip over the tropical oceans are kind of sparse and not frequent, or they have been in the past at least. So therefore it's tough to estimate this apparent scaling. And then we only have about like 20 years or so of like high resolution, consistent precip estimations over this, all of the tropics. And so it's also then tough to estimate the climate scaling. And so this climate scaling, I'd say, is probably what most people who look at tropical cyclones are most interested in. How are tropical cyclones changing with climate? And so most studies in the past have just basically taken a historical model simulation, compared it to like a future climate model simulation. And so many of these studies have been done. They were kind of summarized in this one paper, Knudsen et al. 2020, which found that on average, near storm precipitation in tropical cyclones will probably increase about 14% per 2 Kelvin of warming. So that's about in line with the Clausius-Clapeyron relation on that climate timescale. And so the research question I've been working on is, I have these idealized simulations, model simulations, which I'll talk about on the next slide. And so I kind of wanted to take these and see if I could try to understand how TC precipitation is responding to real world climate change. Could I maybe use these idealized simulations, kind of compare them to more realistic simulations, and then also compare them to observations? So briefly, just to talk about the different data sets I used. First, the idealized model simulations. So they're run with the community atmosphere model, which is part of community Earth system model. It uses the protocols of the radiative convective equilibrium model intercomparison project. So all of these models are in radiative convective equilibrium, kind of just a simplification of the tropical atmosphere, except the one difference is I add rotation to these models so that tropical cyclones actually can form. And so these simulations have globally uniform SST. And so I have 11 simulations with SST varying from 295 to 305 Kelvin. The horizontal grid spacing is about 28 kilometers. So these are, for global simulations, these are pretty high resolution. And since there are RC simulations, there's no seasonal or diurnal cycles. Next, we have our more like Earth-like or realistic model simulations. So these are run using the same model, CAM, the same horizontal grid spacing, about 28 kilometers globally. These simulations have been used to study TCs in the past in a couple different papers. And so I have two different simulations. I have a historical simulation. It's an atmospheric model intercomparison project simulation. So it's for 1980 to 2012. And then I have a RCP 8.5 simulation, so the future simulation for 2079 to 2099. And then observations. So I only have observations for 2001 to 2020, so about 20 years. I use the IB tracks dataset for TC tracks and intensities. I'm using the eMERGE satellite product for precipitation. And then for SSTs, I'm using the NOAA optimum interpolation database. And so I'll note that for my analyses in the next couple of slides, I only look at TCs that are between 5 and 20 degrees latitude, because I'm trying to focus on the area where the TCs in these idealized simulations are kind of most likely to be similar to real world tropical cyclones. So that would be in the tropics. Okay, so first, I simply am looking at what are the SSTs that we're seeing under these TCs in these different data sets? Can we compare them? So first, so observations are in the blue. So this is kind of showing us like how many TC counts or TC samples basically do we have over different SSTs. So we see in the observations, most TCs occur over like 299 to 303 Kelvin. The historical AMIP simulation, so this kind of purple color, compares pretty well to observations. Generally, there's similar SSTs, which is good. When we look at the future simulation, we see that it's shifted, which is the pink one. It's kind of shifted from the historical one by maybe about 4 Kelvin. So that's kind of how much these SSTs are warming up by the end of century. And then the RC MIP simulate or the RC idealized simulations, we see kind of have TCs form at all these all the temperatures that we ran them with. Next, looking at TC intensities. So we look at two different measures of TC intensity. On the left is the maximum wind speed, and on the right is the minimum sea level pressure. And so we see that generally the models actually do simulate TC intensity fairly well. There's a little bit of underestimation of intensity, kind of as expected with global climate models, but not too bad. So that's good. That's a good sign that these TCs are kind of at the same intensities. They're pretty comparable. So next, I looked at radial profiles of precipitation for TCs, and I split it up by the sea surface temperatures that the TCs were over. So as I said, I'm still working on this work, so I actually don't have the future AMIP simulation in the next two plots, unfortunately, but I'm adding them pretty soon. And so what we see here is that obviously we see the highest rates of precipitation close to the center of the TCs. We do see that compared to observations, the models do pretty well in simulating kind of these highest precipitation rates that we see in observations, which is good. One thing that I notice here is that kind of the way that the profiles respond to different sea surface temperatures is a bit different. So, for example, in the RC simulations, we see big changes in the highest precipitation rates in the inner core of the storms. When we look at the historical AMIP simulations, we see there's change in the inner core with SST, and then also kind of in the outer part of the SST of the TC. Sorry. And in the observations, we kind of see this almost uniform increase in precipitation rates with SST almost over the entire profile. So it's just kind of interesting how the response is a little bit different in the models compared to the observations. And so next what I did was for each TC at each time step, I just calculated the 99th percentile TC precipitation. And then I divided that, I kind of binned that by what the SST was underneath the storm. And so same thing here. So blue is observations. This purple is the historical AMIP simulations, and then the black is the RCE simulations. And then these background lines, so this gray dashed line is showing the Clausius-Clapeyron rate, so a 7% increase in precip per 1 degree change in temperature. And then the red line is showing double the Clausius-Clapeyron rate. And so that's just kind of, for comparison of these lines. And so we see that generally, what's noticeable is that the observations and the CAM5 historical simulations do seem to have like a more steep slope, meaning the precipitation is increasing with SST maybe somewhere between the Clausius-Clapeyron rate and the double the Clausius-Clapeyron rate. I do have estimates of the numbers, but I don't have them on the slide. Whereas the RCE does not seem to increase as fast. And remember, one thing is we only have RCE simulations at each 1 degree interval, so 299, 300, 301, 302, 303. Whereas for observations in CAM5, I think these are binned into half degree intervals or something. So there's just more information. So that's why their lines are not as like straight. But generally, yeah, it does seem that the RC simulation, the TCs in the RC simulations are less sensitive to SST change than the CAM5 historical and the observations. I'm also going to add, obviously, the CAM5 future runs to this and kind of see if we can see how the climate scaling may change with this 99th percentile value. And so I did do this. I'm doing the same thing for, instead of 99th percentile value, average TC precip versus SST, and generally the results tend to be the same. So that it doesn't seem to be too sensitive to what metric you use, as far as I can tell so far. Okay, so for my results, just wrapping up. So we see that the TC intensities and their structures appear to be pretty consistent between this modeling hierarchy that I'm using and also to observations. Again, for the apparent scaling or kind of the instantaneous scaling of extreme precip and temperature, the TC precip seems to be a little more sensitive to SST and observations and the AMIP historical simulations than in the RC simulations. I didn't show this today, but I've also done some work looking into kind of breaking down this increase in precip into thermodynamic contribution. So that's just the increase in precip because of the increase in atmospheric moisture as the air warms versus a dynamic contribution. So basically an increase from TC intensity. And so what I've been finding is that it seems like the majority of the change with SST comes from the thermodynamic contribution in both models and observations. So just from that increase in moisture. And now I'm still exploring how we could possibly use these RC simulations to explore the climate scaling between TC precipitation and SST, and trying to understand maybe could we use these RC simulations to project TC precipitation increases as the Earth continues to warm with climate change. And so I'll just advertise. So this paper that I have up here is all about those idealized RC simulations and how the TCs and their precipitation change with SST. So if you're interested in that, that's the paper. As I said, I hope to get a paper about this work or submitted within the next month or so. I'm happy to take questions now or at the end of this, and also my email is up here if you want to reach out afterwards. So thank you everyone for listening.
Okay, great. Thanks so much, Alyssa. That was a great presentation. I think we're gonna hold all of the questions for the discussion at the end. So if you have any questions for any of the speakers, just go ahead and put them in the chat at any time. And then at the end, we'll all have a big group discussion on all of this. So let's move on to our next speaker, Fraser King. Fraser is a PhD candidate at the University of Waterloo and studies the interaction of, remote sensing and machine learning of precipitation with a background in computer science and statistical modeling and a focus on remote sensing of snowfall. So with that, I'll let Fraser take it away.
All right, yeah, thank you for the introduction. So today I'm going to be talking about a model that we've been developing over the past few months called ECSPrecip. This is a neural network that we were working on to relate information from the lower atmosphere, reflectivity data, to surface precipitation. And I always start off these talks by highlighting the model on the right here. It's not just a fancy image. This actually is the model we're working with. It's just kind of cool to see the incredible complexity that we get from some of these neural networks that we're working with different layers interacting with one another. I think it's really visually quite interesting to see. Okay, so a little motivation. As we all know, snow is a very important contributor to the global water energy budget. It has huge implications in many different regions of the world, especially sort of where I'm from for flood forecasting and mitigation, as well as water resource management, thinking about groundwater recharge, runoff, that sort of thing. However, in Canada, especially where I live, the distribution of in situ measurement sites is quite sparse, especially as you move further north. And there's these large unobserved gaps where we really don't know how much snow is accumulating there. And so you can use models or you can use reanalysis products to try to fill those gaps. However, these also have their own uncertainties and biases. And so we're always thinking about ways we can supplement these data sets to try to understand what's happening in unobserved areas. And so this kind of leads into the project that we've been thinking about, which I alluded to on the previous slide, where we're relating information from surface radars and potentially spaceborne radars later on to surface precipitation using neural networks and machine learning. And so this work really builds off of a previous study, which we just had published in JAMC, where we looked at data from GCPEX, which was a GPM validation experiment near us. And we looked at the Vertex radar. This is an X-band radar that was situated at the site. I'm showing a few profiles of that on the top right here. And we wanted to see if we could relate information in those verticals, so the different bins in the vertical profile, with whatever is accumulating on the surface below. And so on the bottom left here, I'm showing a little time series for the accumulation period at the site with the reflectivity values in red for each of the bins and their mean value, as well as the black being the precipitation accumulation on the surface. And if you really squint, you might be able to see some relationship, but we figured this would maybe be more suitable for a machine learning method. And so this proof of concept study, we fed it into a random forest, nothing too overly sophisticated, and we found it actually did a pretty good job at relating information from that vertical profile to the surface accumulation. And we also were able to learn from the model and found that really within that bottom sort of 1.5 kilometers is where the model found the most significant contributions to high model accuracy, which we thought was really interesting. But this was just a proof of concept and we wanted to build on it. And we thought, hey, we have more than just a single site of data. So let's try to incorporate more information and feed that into a model. And when we're thinking about deep learning, so instead of just a random forest, now these layers, or these models with neural networks with multiple hidden layers, they really like data. And so I have sort of a simplified summary on the left of what happens with deep learning. When you feed in additional data, it typically scales, not quite linearly, but almost as you feed in more information, and you're able to get even higher performance. And so what we ended up doing was looking at a variety of different sites. We picked 9, as I'm showing here, from across the Northern Hemisphere. Some of these are also GPM validation experiments, so you might recognize those and others are not. We have site data from over 8 years, from 2012 to 2020. And I've plotted where we have actual observations on the right. And so you can see some periods where we have overlap, which is great, but others where we maybe only have data from a single site. And that was actually done on purpose because we were curious about, we wanted to develop a robust model. And so we were curious to see how the model would learn if we provide data from, individual locations at different time periods, over different seasons at different points around the world. And what we ended up using at each of these sites was the surface radar and MRRs. This is a micro rain radar pictured on the left here. And then we were relating this information to Pluvio 2 gauges that were collocated at each site. And what we were feeding into the model were the observations from the MRRs, the total reflectivity, Doppler velocity, and spectral width, which I'm showing in the center here. And so what this kind of looks like, if we put it all together on the right here, for each of the different sites, these are the different rows on the figure here. And you can see we have in red, the reflectivity, purple spectral width, and green Doppler velocity. So these are the MRR variables for each of these different sites. And, as you move up for each of these different subpanels, this is moving up in the atmosphere. These are just frequency histograms here. Or heat maps here. And so what we were really looking for is to see a very sort of distinct pattern in terms of the spatial structure of reflectivity values at each of the different sites. And so we kind of see that here, where, for instance, the observations at Olympics are very distinct from what we would see at Joyce, for instance. And this is, again, sort of in hopes of creating a more robust model. And we were also incorporating some atmospheric data from ERA 5, and those variables are on the right here. So this is in blue, we have temperature data as well as wind velocity to try to understand and provide additional context to the model in terms of the type of synoptic events that might be occurring at each site. And so we have a very sort of generalized or simplified, pipeline of how this data all interacts on the left. We basically feed in the MRR, we do some k-mean clustering, which I'll talk about in more detail later on. This is also we also provide the ERA 5 data, pre-process it to 20-minute intervals. So we're really looking at sort of 20-minute average accumulation at the site. Feed that into ECSPrecip with the pluvio2 data as the response variable, and we get an estimate of surface accumulation in both either snow or rain. And that's really another important part of this model. ECSPrecip isn't specifically designed for a specific phase. It's sort of phase agnostic. It knows nothing about whether it's snowing or raining, and it's sort of able to back out the amount of accumulation on the surface with none of that knowledge explicitly provided. And just so you don't have the black box to think about, this is what the actual ECSPrecip model structure looks like. I won't go into too much detail here, but we can chat about it more after if you're interested. It's a pretty typical 1D convolutional neural network. So we've got the feature extraction components at the front here, some dropout, and then we have our fully connected feed-forward regression component. This is like the MLP, which spits out a precipitation estimate at the end. And so in terms of results, the first thing we looked at was comparing ECSPrecip performance to other machine learning techniques to see if we're really gaining anything using this more complex method with the CNN. And so what we ended up doing was comparing against the random forest, which is what I was talking about from our previous work on that second slide of this talk. We incorporate that model here as well to see if we're gaining any performance with this ECSPrecip model. And so to evaluate that, what I've got here is a time series for each of the different sites concatenated together in time of accumulation on the y-axis. And we've got the black, which is the pluvio estimates. ECSPrecip is the gold, and then the random forest from the previous work is in green. And so if you take a look at the image here, you can see that the random forest is able to capture some of the peaks and troughs in the data. However, at areas like Joyce, for instance, it really sort of flattens out, and we get this estimate closer to the mean, something you might expect to see with sort of a linear estimator, for instance. And then at areas like Olympics, where we have these really intense precipitation events, it also performs with poor accuracy compared to ECSPrecip, which is more capable of gaining or of properly estimating those high peaks of extreme precipitation. Both models fall short in some areas as well, and then get into that in more detail. For instance, at Marquette, where we've got a lot of mixed phase precipitation, they both don't do as well, and this is an area we're looking at improving in the future. But the key sort of takeaway is that comparing the ECSPrecip model to the random forest, the statistics on the right highlight the main differences there. We have a much lower mean square error value, better R square. Both of those are about a 40% improvement over the previous model. And so this is really promising, we think, from these sort of initial comparisons here. But when you're thinking about precipitation and reflectivity values, you might immediately think about these ZS and R relationships. These are power laws where you're relating these sort of empirical bespoke power laws relating information from a reflectivity bin to surface accumulation, either snow or rain. That's the SRR. These are often used in literature and can do quite a good job, but due to the assumptions in the actual generation of these power laws, which are related often to things like the regional climate, fall speed of the particles, shape, size, distribution, that sort of thing, they don't often generalize well to new climates. And so what we ended up doing was selecting a handful of these ZS and R relationships that were also trained on K-band radars, the same as the MRR we're using here. And I'm plotting on the left these relationships. These are the individual relationships for the sort of total accumulation. These are total cumulative curves here over the full period, with red showing snow and blue showing rain. These are the colors we'll use for snow and rain for the rest of the talk. And then in black, again, we've got our pluvio estimates, and in gold, we've got deep precip. And so the takeaway here on the left is that the machine learning methods end up, or the deep precip model here ends up doing a bit of a better job than what we're seeing from any of the individual ZS and ZR relationships. And while some may align better at certain parts, overall, the strongest performance is with the machine learning techniques. And this is again reflected in the mean square error plots or bar charts on the right here. These are logarithmic scale, just to highlight that, where we've got each of the individual ZS relationships and ZR relationship MSE values, and then deep precip is substantially lower than any of those, with the strongest performance increase with rain specifically here. And that's likely a result of the higher, the larger sample of rain data that we have compared to snow with what we were looking at from these sites here. And so we also derived our own power laws, precipitation power laws at each of these sites to see if deep precip does better than those. And it's a similar sort of story. So on the top here, again, we have a time series showing deep precip versus all of the different ZP relationships. And those are shown within the light graded lines, and they're mean in the dark gray line here. And again, it's sort of a similar story where certain power laws perform better when they're applied to similar sites with similar climates, but a model or a relationship generated for Olympics doesn't typically do as well at Joyce, which is a very different climate. Meanwhile, deep precip is more able to handle that change in accumulation across all these different sites. And this is also reflected in the bottom MSE plots again, where I'm showing basically the MSE values for each individual ZP relationship when trained at a single site and applied at different sites. And so, if you take the GCPEX site, for instance, here, the best performing model here is the ZP relationship derived at that site, which makes sense. But deep precip is close behind. That's the bar on the right in orange. And this orange bar, if you look across all of these different sites here, is typically either the lowest or just behind the site with the ZP relationship trained or derived at that location. And so this again is promising that we're developing a model that can capture accumulation across many different climates here. And so you might say, well, is your model just overfitting? That's always something we're concerned about. We did a lot of work to make sure that wasn't an issue here in terms of how we were doing our hyperparameter optimization. We did a lot of regularization using dropout, kernel constraints, and early stopping, that sort of thing. And I won't go into too much detail about the plot at the bottom just for time, but one thing you can always do with these types of experiments is this leave site out cross validation, where we would leave an entire site out of the training data, for instance, ice pop, and then we would train the data on all the other sites of information we have and then apply it to ice pop. And so the model then knows nothing about what's occurring at that site, and you can see how well the performance lines up to the other ZS relationships or ZR relationships when applied there. And so when we do this across all sites, we see that, well, the best performance is when you're using data from each site. The deep precip model actually still outperforms the other ZS and ZR relationships on average, which again is further sort of reinforcing the robustness of this technique. And so just to kind of wrap up here, one other thing that I think is really interesting with these type of analyses is not only thinking about developing this operational model, but also trying to learn from the model. And this has come a long way in recent years in terms of model interpretability with deep neural networks. And so we use a Shapley analysis where basically we look at different combinations of inputs and we see how that impacts model accuracy. And what I'm showing here are different precipitation intensity groups from the MRR data we have across all sites. These are clustered into 4 different sort of main groups here using the k-means clustering I mentioned earlier. And then when we look at the importance of each of the individual predictors, which are the columns here, the darker color in the column, the shaded regions, represents an area where the model sees really important information in its retrievals. And we can see from here that it's actually a mixture of both near surface and far bins. And it's not just reflectivity, but it's some of the other MRR variables like Doppler velocity and spectral width that are very important, and especially Doppler velocity in the upper bins as we move to more intense precipitation events, which is very interesting. And so I think this is applications for, thinking about blind zone motivation and that sort of thing in future studies, just because our models say this is a very important region. As well, I think there's potential application to apply this to spaceborne data, where we've got these huge data sets from satellites like GPM or CloudSat and that sort of thing, to see if we can apply this in sort of a global scale. And so, yeah, that's all I have for you guys here today. I won't go over the summary, but just for time, I'll thank you for listening, and I guess we'll take questions at the end.
Okay, great. Thanks, Fraser. That's a really interesting talk. So next, we have Yoonjin Lee, and she got her master's and PhD in atmospheric science at Colorado State University, and is currently a postdoc at SARA, also in Fort Collins there. So with that, go ahead, Yoonjin.
Thanks, Lindsay, for the introduction. So the title of my talk today is using GOES-16 ABI to detect convection, estimate latent heating, and initiate convection in a high resolution model. And as the title suggests, you can see there are three parts in this study: detecting convection, and then estimating latent heating, and then eventually initiating convection in the model. And in the next slide, I'll explain how all three things are related to each other. So during the short-term forecast, usually the operational model uses ground-based radar data to initiate convection. For example, NOAA's operational model called HER model initiates convection using the next-red radar reflectivity. And how it's done in HER model is that during 1 hour pre-forecast run, the latent heating derived from the next-red radar reflectivity is added every 15 minutes. And then adding it for an hour, the model is run freely after an hour. Excuse me. So the radar reflectivity is converted to latent heating using this empirical formula that has C in this Q sub S term. And these latent heatings are ingested in the regions where it has reflectivity greater than 28 dBz to initiate convection. But even over CONUS regions where there is a dense ground-based radar network, you see that there are places where it misses ground-based radar data. So the only observation that has similar temporal and spatial resolution to these ground-based radar data is geostationary satellite data. So this whole work is using geostationary satellite data to do the same thing as we do with the ground-based radar to initiate convection in the regional model. So this talk consists of three parts. First is detecting convection, as the HER model uses this 28 dBz threshold, and then latent heating estimation using GOES-16 data, and then eventually initiating convection using this latent heating retrieved from the GOES-16. So the benefit of the current operational geostationary satellite is GOES-16, and the benefit of using GOES-16 data is that it has really high temporal resolution data. I'm showing you two animations here. On the left is the GOES-16 channel 2 reflectance visible imagery, and then on the right is channel 14 brightness temperature maps. And with this 1 minute imagery, we can see where convection is occurring, because if you look at these clouds, vertically glowing clouds, you can see that there's a decrease in brightness temperature. And this is the indication of that there is a vertically growing clouds. And the other features of mature convective clouds are high reflectance and low brightness temperature. And you see in this very high spatial resolution data, you see that there is a bubbling cloud top. So using these features of convective clouds, we can find where convection is occurring in geostationary satellite data, despite the lack of the vertical information from visible and infrared sensors on geostationary satellite. So we developed two methods to detect convection. One is using non-machine learning based methods, and it's published in the Atmospheric Measurement Technique journal. And the other one is using machine learning model. And in this talk, I'll briefly go over how how this model is developed. So the input and output of this convection detection model using GO16 is shown here. So we have inputs of 5 visible images of channel 2 reflectance with 2-minute intervals. And this channel 2 reflectance is related to cloud optical depth. That's why we use channel 2. And the other input data we use is 5 brightness temperature images at channel 14. And channel 14 is usually related to cloud top temperature. And so the input images are 2-minute intervals, and the model is trained against MRMS precipitation flag. It's a radar-based product, and it determines whether there was convection or whether there was convection or not. So the model architecture is shown here. It's an encoder-decoder model. So the upper part is the encoder part, and the lower part is the decoder part. So the initial input is GOES channel 2 reflectance. So there are 5 images of channel 2, and there are 2 convolution layers, and then max pooling, and then 2 convolution layers, and the max pooling. And after 2 max pooling layers, this is where we put GOES channel 14 brightness temperature maps. And this is because channel 14 brightness temperature has 4 times coarser resolution than the channel 2 reflectance data. So after going through the encoder part, it goes through the decoder part, and the truth we consider is the MRMS precip flag, and value of 1 being convective and 0 being non-convective. But since we use sigmoid function at the end, the predictive values will vary between 0 and 1. And so after training this model, we had to decide a threshold to detect convection. So if the threshold was 0.5, then these 4 grid points will be considered as convective grid point. But if the threshold was 0.8, only these 2 grid points will be assigned as convective. So this is done. Determining threshold is done after the training. And this is the overall machine learning model results. It's showing probability of detection and the false alarm rate in this plot. So the different dots show results choosing different threshold for determining convections. And you can see that this dashed line is a critical success index. So the larger critical success index, the better the model accuracy is. And you can see that these results show that it achieved a decent critical success index. And in the next slide, I'm showing you one case study to just to give you an idea how well it does. So on the left is the MRMS precip flag, which is a truth, and on the right is the model prediction. So on the left figure, the pink regions are convective regions by the MRMS product, and the navy regions are the non-convective or the stratiform regions. And on the right, the colored regions are the regions that are detected as convection by the model prediction. So if you compare these pink regions with these colored regions, you can see that they agree really well. So the model is doing overall really great, comparable to the radar product. So then after we published this paper, while I was doing my postdoc, I started thinking, how about we remove cloud motion in the input data set? How does it affect the model results? So there will be a poster in collective medicine meeting about using optical flow to remove storm motions and how it affects to detecting convection in the machine learning model. So now that we have detected convection, the next step is to retrieve latent heating from using GO16. And usually the latent heating retrieval is done using active microwave sensors such as DPR on GPM satellite. And usually what they do is they have a lookup table made of model simulations, and then they try to look for the latent heating from the lookup table. So that's done similarly in this work. So we created a lookup table using WRF model simulations and CRTM model. And this lookup table is based on cloud top temperature, which is channel 14 brightness temperature. So the lookup table is summarized in this plot on the right. So each line represents a latent heating, vertical profiles of latent heating for each cloud top temperature beams. And these beams are every 5 Kelvin. So once we find convective area using convection detection model algorithms, the latent heating profile is assigned to each convective grid point by searching a profile in this lookup table using its cloud top temperature. So in the next few slides, I'll show you some results applying these latent heating retrieved from the GO16 in a convective scene. This is a case study where there was a convection moving southward. And these two maps are the vertically integrated heating rates from GOES and from next-red radar effectivity. And these are the latent heating used to initiate convection in the model forecast. So there are several things to note if you look at these plots. On the left is the next-red total heating, and on the right is the GOES total heating. And the reason why I'm showing the total heating rate is because these are the total amount of heating that will be ingested in the forecast model to initiate convection. So first thing to note is that the next red tends to have wider area of convective regions, and that's because they use 28 dBz as convective grid point. And the other thing to note is that if you look at these two green box regions, next red tends to have really high heating rates in few grid point and then very few heating rates elsewhere. And if you compare these regions with these heating rates on the right, the GOES tends to have heating rates spread out over a convective cloud. And in the yellow box regions, GOES didn't detect convection, so that's why it didn't show heating rates in these yellow box regions. So in the next slides, I will show you the results using this. Oops. I'm sorry. I'm sorry, it just closed.
It's no problem. We're still way ahead of schedule, so take your time.
Oh, my laptop is really old, so it crashes every time. Okay. Hopefully you can see my slides. Oh. Okay. So I'm showing you the 1 hour rain accumulation forecast results after adding these heatings during 1 hour pre-forecast run. On the upper right is the MRMS gauge corrected QPE, which is the truth we consider. And then on the upper left is the WRF control case where we didn't ingest any of the heatings. And lower left is the adding next red heating, and lower right is adding latent heating from the GOES 16 data. So if you see these green box regions in the control case, they didn't really develop a convective clouds over here. But if you compare it to the next red heating experiment and the ghost heating runs, you can see that they both created convective clouds or produce some amount of precipitations in these regions. And if you see these red box regions, control case, it didn't have anything, and next red didn't really have anything because, as I don't know if you remember from the previous slides, but there wasn't much heating in these red box regions. But ghost heating rate were able to produce some amount of precipitation in these regions. And similarly in yellow box regions, on the other hand, the next red heating rate were able to create some precipitation here, but since ghost didn't really detect convection in this area, so it didn't produce any precipitation. But overall, both next red and ghost heating rates were very effective in initiating convection. And this is the overall friction skill score to quantitatively show compare the results. We use friction skill score. It's a neighborhood-based precipitation verification matrix. So the larger FSS, the better the model forecast is. So the black line is the control run, and the blue line is using ghost 16 latent heating, and red line is using next red heating rates. And you see that although ghost heating rates weren't as good as next red heating rate runs, at least it was able to improve the forecast results. And in the earlier slides, I showed you the lookup table only based on the cloud top temperature, but the lookup table can be further divided into according to the composite reflectivity. And if we have information about composite reflectivity from ghost 16, then we can use this lookup table to further to assign latent heating in more detail. So there is a machine learning model developed by Kyle Hilburn at Sierra. It produces composite reflectivity from using ghost 16. So this gremlin model is combined with this lookup table to provide a vertical profile of the reflectivity. So this lookup table can also provide reflectivity profiles as well as the latent heating profiles. And in this case, we use the vertical profile of the reflectivity. And these combined products are, we provided this to Amanda Beck at NOAA to do a retro run for a certain period of time. And this is a slide from Amanda's AGU talk last year. And this is showing results using this gremlin latent heating combined product versus using MRMS-based heating rates. So on the right is the Rufus forecast, the operational model forecast that didn't really produce convection here if you compare with the MRMS composite reflectivity. But if you look at these red regions, the MRM, even if we had MRMS-based heating rates, it didn't really produce convection in this case. But with the gremlin latent heating product, we were able to produce convections better than the MRMS-based heating rates. And this is also another slide by Amanda at the AGU talk. This on the right figure is showing the critical success index for the CONUS regions. And the red color is CSI without any latent heating adjustment. And the blue line is MRMS based adjustment. And then the pink line is, or the purple line is a gremlin based adjustment. You can see that the gremlin does really similar to the MRMS based adjustment. And especially this lower right figure is only over West Conus, where there is less radar coverage. And in this case, the gremlin were able to do better than the actual MRMS-based latent heating products. Yeah, that was all I wanted to say. And we'll take any questions. Let me stop sharing.
Great. Thanks, Yoonjin. thank you, all of our speakers. It looks like we have quite a few questions in the chat, so open up for some discussion. If anybody has a question they want to ask.
In chat, we have a question for Alyssa. So you might have seen, it says, it's from Jackson, and he's asking if you limit your analysis to 5° to 20° latitude range, would you undercount TCs and skew their TC precipitation for RCP 8.5 simulation, in which we may expect changes in the geographical range of the future TCs?
Yeah, this is a really good question. I actually hadn't thought about this too much, so I'm glad you brought it up. My first intuition is that I don't think TCs are supposed to shift their range drastically, so maybe a degree or so at most. So I don't think it would make too much of a difference. But I do have the tracks of the TCs obviously already, so I probably will look at the average latitude of genesis maybe between the historical and the future simulations. That probably would be something good to look at. So thank you for that question.
Thank you. Jackson, do you have any follow-up question on that? You are muted. Okay. Lindsay, you want to take next question?
Sure, yeah. So Lisa had a question for Fraser. Did you try add any other parameters from ERA 5 other than temperature and wind velocity? And if yes, which ones did you add?
Yeah, no. So yeah, that's a great question. Actually, I can probably answer the next two because they're kind of similar, both about inputs, about what we were feeding into the model. So we did try a few different things. I mean, it's always a bit of a balance between what you give it, because you don't want to do the machine learning for the machine, but I'm not against including more variables. So we did think about this a little bit, but we didn't end up including any other ERA 5 variables yet. I would be curious about doing so in the future just to see what works well and what doesn't, and then potentially including or excluding those based on sort of their feature importances. And then in terms of Jackson's question as well, thinking about other inputs, things like the climate classifications, that sort of thing. We haven't done that yet, but both of these are things I think we'd like to explore in more detail in the future. We were also curious about adding things like information about cloud top height, sort of where we think the where the precipitation phase is in terms of whether that's solid, liquid, or mixed, and then even thinking about things like macrophysical properties that we could feed in, because these are often huge components of the traditional empirical models. And so I think there's a big space, and there's a lot of different inputs we should be considering, and have not had the chance to do so yet. So hopefully these are something we can include sort of in future iterations of the model, and experiment to see what's important and what's not.
Okay, yeah, great. And
we can ask next question to Yoonjin.
Yeah.
So I had a question for you, since this is highly unbalanced data, did you face issues with false alarms?
Yes.
And how did you deal with that?
Yeah, so like you say, it was really unbalanced. And so what we did is we only used regions where there was precipitation, at least one grid point. So we eliminated all the clear sky regions. And the reason why we did that is because the clear sky regions are involved in the precipitation scenes anyways. So that way we could reduce some of those imbalance in the training.
Okay.
And I'll take Fraser's question. I used MSE in the beginning, and then after that I also use adaptive loss function, which is I would train it using MSE first, and then since we wanted to improve probability of detection, after training once using MSE, we train again with the additional term in the loss function where we punish more if there was misses. And it didn't really improve huge, but it improved a little bit. So we're not really sure if that had a huge impact or not, but. And then I'll also answer Jackson's questions. I didn't use water vapor channels in the machine learning model, but I used water vapor channels in the non-machine learning based model. And like you said, it's only available during day. It's only for daytime because I use reflectance data. Then Lisa's question, yeah. So yes, Next-Thread can miss anything, and we see some of those cases. So we eliminated radar data with bad quality using radar quality index. So that was a huge problem when we train, because we can't have the model learn false things if the radar wasn't true. So, but that was the only thing we can do, just to eliminate the radar data with low quality.
Thank you, Yoonjin. Fraser, we have a couple of more questions for you. Do you want to address them?
Sure, yeah, which ones did I miss here? Sorry. Oh, Alyssa, okay, sorry, yeah. Do you think ECSPrecip could have any applications for precip forecasting? Yeah, so the way it's constructed right now, we don't really do any forecasting into the future. The hope with this model, this iteration at least, is that with what we've developed, you could feed in data from an MRR. So say you have a site where you're curious about what the precipitation looks like, and maybe you don't have a collocated gauge. The idea is you could feed in sort of either historical data or data you're getting, minute by minute, to get an idea of what's precipitating on the surface there. I think it's an interesting question to think about it in terms of forecasting, but we would probably change the model slightly to do something, maybe with an LSTM or something along those lines that works a little bit better with temporal, the temporal aspect of the data, because currently we don't really have any geospatial, or temporal component to this model at all.
Yeah, that's cool. I was just,
yeah.
well, I guess I kind of a follow-up, but I was just thinking, like, if you had output from like a forecast model, GFS, say, or something, like, would you be able to feed it into your model and kind of compare the output of ECSPrecip to the output of the model precip? I think that'd be kind of interesting if they were like really different.
Yeah, no, absolutely. Anything where we can get sort of information about that lower atmospheric reflectivity, we could use that as input, see what gets spit out from the model, and then do some comparisons. That'd be kind of interesting.
Yeah, that'd be cool.
Yeah. Thanks. Yeah. I guess I'll answer. I think Yoonjin's was the only other one I missed. Why did you do k-means before putting into machine learning model? Could you elaborate more about this? So maybe I wasn't super clear about that in the talk. That's my mistake. We don't actually use the k-mean clustering output as a predictor in the model. That's just done at the beginning so that we have an idea of where that reflectivity profile would lie in terms of its intensity for the Shapley analysis at the end. So we use that just to basically do subsections of the input data we have. And then when we've got that sort of broken up, we run the model with those different subsections to see how performance changes when we're leaving certain predictors in or out, that sort of thing. So it's not actually a predictor in this sense, but it's just used for interpretation later on.